Hi guys, I'm here with Dr. Portillo. We are about to start week 3. So, yeah.
Hello.
What we're going to learn today?
Today we're going to have an introduction to C++, in where we are going to end it up with learning how to define classes.
Okay.
C++.
And tomorrow?
And tomorrow we will introduce ParaView.
Okay. Thank you so much. I was just wondering if this bar here in the code, like, is just for test. This thing, we don't need it, right?
Yes, the thing is I'm commenting those tweets, so I don't have to start typing every time that you run the code.
Okay.
And instead
So
of doing
just
that, I'm
putting this.
Do you see over there?
Hi guys, we are here in the week 3 of the NuSTEAM program. I'm with Dr. Volodymyr.
Hi, yes, we are currently doing a computational physics week of the program. I'm assistant professor at University of Houston, and this week we are covering the basic techniques and tools which are commonly used in high energy physics, and we are doing some cool examples here related to various aspects that we use in our research eventually.
Yes, thank you so much, Professor.
Absolutely.
I'm going into my senior year, so like I'm talking.
Hi everyone, week 3 just ended and I'm really excited to show you all the things we worked on this week. This week, Dr. Portillo keeps encouraging us to still learning more about the programming techniques. So once again, we code the quadratic equation solver, but this time we work from his version of the code. So we edit the file to include loops so the user can solve multiple equations without restarting the program or has to end the kernel. Then we added more functions and called them from the main loop. finally, we work with classes, and I learned so much about object-oriented programming since I haven't worked with that before, and I found that private class members can be accessed or modified directly by the user, while public members can do it. So they are the ones that interact with the user. We also add a new language to our toolbox, the C++ language, and it's still one of the most widely used programming languages in science. So we translate our quadratic equation program from the Python to C++, and honestly, for me, the syntax is more complex. I already knew a bit of C, but C++ has a lot of specific details that are confusing at first time. For example, we even had to use pointers to return multiple values from a function. So yeah, we translate the whole code from Python to C++ and it works, so I'm very glad for it. Then it came to the fun part. We started to use ParaView. ParaView is an open source software for visualizing scientific data, and we practice with some pre-made examples files that are located in the ParaView program. We learn how to use clip and stylize tools. We create ISO surfaces, and even we work with the time step to make animations. So for this week, our homework was to create an animation using lattice quantum chromodynamics data, which show us how quarks and gluons interact in the space-times, and Dr. Portillo gave us the data, and we used ParaView to visualize it and animate it, and here's what I made. I work a lot for this animation, but I think it's really cool. Okay, so this week we also had the chance to meet Dr. Volodymyr Bobchenko, who showed us how modern physics research can be done using computational tools, and that's what we learned this week. We learned how to download and run open source softwares. In fact, we work with his own GitHub repository, Thermofist, which is using hadron gas model applications, and I figured out how to clone the repository, installing CMake and compile the program to get the interaction data between different types of particles. We also explored his Jupyter notebook plotting data, super important for scientific communication. We use matplotlib, that is a library from Python, and we discussed the floating point precision. Is the representation of 32-bit or 64-bit, whereas 64-bit floating point number has double precision. It stores about 16 decimal digits, but isn't exact. So errors can occur when representing numbers. For example, 1.1 plus 2.2 might not be exactly 3.3. It will be 3.0000000, so many zeros, and 3. So there is an offset in the calculations, but we can correct this with the epsilon approach. Is basically the difference between the two numbers very small. For example, when using the quadratic equation, if AC is less than b squared, then we are subtracting of two large numbers, leads to precision loss. That's why we rearrange the quadratic formula in this way to avoid the precision loss. Other types of application in computational physics are numerical integration and derivatives. We have many techniques for integration that we can follow. For example, the rectangle rule, consisting of C integration as the area under the curve of a graph, and drawing many rectangles with minimal width approximately to 0 and taking the area. Another technique is the trapezoidal rule, as the same way as in the rectangular rule, we approximate the area of the trapezoid, and we can see that it minimizes the error of the area on smooth functions. Then we have the Simpson's rules that combines both methods using parabolic interpolation, basically finding the quadratic formula that fits in different points of the graph, so it's more complex to implement. To solve equations, for example, x plus e to the negative x negative 2 equal to 0, we can use numerical methods to find the root by iterations. For example, the bisection method, consisting of taking the midpoint of a desired interval, evaluate each one to know if the root is there, and repeat the process until you achieve the desired precision. By solving this equation, the program takes 35 iterations to achieve it. Then we have the secant method, where you pick two starting points near where you think the root is. Then you draw a straight line through those 2 points on the function. Where the line crosses the x-axis, it becomes your new estimate for the root. Then you repeat the process using the last 2 estimates until you get close enough. It's way much faster than the last method, but without guarantee signs it failed to converge, if not approximating the range. Finally, we have the Newton-Raphson method that starts with an initial guess using the Newton-Raphson update formula to compute the next estimate. This uses the derivative, and when it's close to 0, it starts to fail. For this method, it took 6 iterations of the program to work. Then we use random numbers, actually pseudo-random numbers, since the computers can produce random numbers, but it's something related. So it's another topic we touched in this week. We can use the Monte Carlo methods to detect the area under the curve of a graph. We can estimate the area by sampling points uniformly in a rectangle, counting the fraction of points under the curve given by the integrand f of x. Basically, we shoot random points under a curve and estimate the area based on how many points fall under it. We can even compute pi with this method. Creating a circle of radius 1 and plotting points, we can get the value of pi. It's not the best effective way to do it, but it's at least one way. We can even compute the volume of different dimensional balls using the Monte Carlo method. We did it, but it took the process too long to take it. At least with the rectangle rule it does with numerical methods, but using Monte Carlo method is way more efficient and it took less time to do it. So here in the program you can recognize that the second dimension you find pi, and it's correct because we are using a circle of radius 1. And then in the dimension 3 you can find exactly the formula 4/3 times pi, since is the volume of the sphere. In other dimensions, I cannot tell you if it's correct or not, but it's an approximation. I love so much this week. I learned so much about how programming really connects with physics and how powerful these tools are when solving real problems. We wrote a lot of code, and I know that it will be useful for my future. Thank you for watching this video, and I guess that I see you next time. Bye!